Hello, and thank you for watching this video. For this project, I decided to capture the work, the force, the acceleration, and all that jazz of a ping pong ball being launched via the flick of a finger. So to start things off, I will switch this to the magnitude of the position over time, which is the displacement. And as you probably could guess, as the ball is flicked, there is a sharp spike in the displacement, and it goes out of frame, so we don't really know what the magnitude of the displacement is. So we shall move on to the important one, which is the magnitude of the velocity. So when the ball is flicked, it immediately reaches the peak velocity right here. Almost immediately reaches the peak velocity of 5.78. You see right here at the bottom of the screen. I'll pause that so you can get a better look at it. 5.78 meters per second, which is the peak velocity. Now if we switch this to the acceleration, again there is a sharp spike in the acceleration because the ball is being launched. We're adding that force to it. And you see that, let me pause the video, this peak acceleration is 65.69 meters per second squared. This collision, right here, the one in the video, is an elastic collision. So the first thing that we're going to find is the force. So the force of the flick equals the mass of the ball times the magnitude of the acceleration of the ball. So we get F flick equals, and I check this on a very official ping pong website, that the mass of a official ping pong ball, a regulation ping pong ball, is 2.7 grams, which is 0.0027 kilograms. Multiply that by our peak acceleration that we found, which was 65.69 meters per second squared. When we multiply these two together, we get the force of the flick is 0.1774 newtons. Now we're going to find the change in kinetic energy of the ball. And by doing this, we'll take Kf minus Kef, I should say, minus Kei equals change in kinetic energy. So we have Kef equals P squared over 2m, also equals, and this is pf squared, which equals 0.0156 squared divided by 2 divided by the mass, which is 0.0027. Leaving us with a kinetic energy of 0.0451 joules. And we also know that our initial is 0 because the velocity is 0. So our change equals 0.05451 joules. So the next thing we're going to find is the momentum of the ball. So we find that momentum equals m of the ball times v. And that turns out to be P equals 0.0027 kilograms times, we had 5.78 meters per second. That was our peak velocity at the beginning there. And this goes out to equal 0.0156 newtons. And because it starts at rest, this is technically the final momentum, and the P initial equals 0 because velocity initial equals 0. So therefore, this also equals change in P. So unfortunately, there's some things that we are not going to be able to find in this experiment, just from a lack of data, a lack of information, and just by the nature of the experiment itself. First and foremost, that is work. Work equals force times displacement, and another version of it is change in energy. Fortunately, the ball went out of frame, so we don't have the displacement. Also, the energy, the total energy, would have been gone from chemical in the finger and a little bit of potential because the ball was raised to get the kinetic, the heat that was created, and the sound. Now, we don't know these, and we don't have the data for that. So therefore, we can't find work, which means we can't find power either, because power is simply work over time. We could find time by looking at the videos and seeing how long the finger is in contact with the ball, providing that force, but we cannot find work.